All right, so today we're going to talk about a concept called approximation schemes. And an approximation scheme is basically an important style of generalization of the approximation algorithms we talked about before. So in our last lecture, we were talking about approximation algorithms, and the main goal was to define what we called a constant factor approximation, or a C approximation. So I say a C approximation is an algorithm that always returns a solution XA, whose cost is less than or so the cost of XA is less than or equal to C times the cost of an optimal solution. Or alternatively, the value of an optimal solution, this is in a maximization problem, is less than or equal to C times the cost of XA. Right, so the top one here is for minimization problems. And the bottom one here is for maximization. Okay, and so this is good. Like it's a good thing to have a C approximation algorithm, a constant factor approximation algorithm. But it might leave you wondering, if there's any flexibility in this. So if I run a C approximation algorithm, it runs in some fixed time, and it gives me a solution that's guaranteed to be in this, within this factor of optimal. But it doesn't seem to offer any additional wiggle room. And something that you might imagine that you'd want is you might say, well, look, I mean, this thing runs and it gives me a solution that's within this constant factor, but I'm okay with running longer. Like I could run twice as long if it allows me to get a better guarantee. And so that's the whole concept of an approximation scheme. The approximation scheme has an error parameter. So you feed the actual algorithm with a parameter that says, here's how close I want to be to optimal. And so here's the kind of the formal definition of approximation scheme. So an approximation scheme goes like this, so definition. So we're going to let P, capital P, be an NP-hard problem. And it has an objective function f. So with objective function f. So f is the thing that codifies either what we want to get the most of or what we want to avoid. So in the case of knapsack, f is the total value of things that we're bringing. In the TSP, f is the cost of a tour that goes around the cities. Okay, so we say algorithm A is an approximation scheme if, given the error parameter, right? So the approximation scheme has, its first input is the problem instance, but then its second input is this error parameter. So given error parameter epsilon strictly greater than 0, A outputs gives an output. So outputs XA that satisfies the following. So the cost of XA divided by the cost of an optimal output is less than or equal to 1 plus epsilon. All right, so before I write the next one, let's interpret this. We're taking the cost of the output divided by the cost of the optimal. And so this is the form that we'll be thinking about for a minimization problem. So this is for minimization. So think this is how it would work for the TSP. And so if our algorithm outputs something whose cost divided by the cost of optimal is less than or equal to 1 plus epsilon, what this does is it means that we can choose our epsilon to make this approximation ratio very, very close to 1. Right? So that's the idea, is you should be able to pick an epsilon, and the epsilon is an error on your approximation factor. And so, in some magical world where you could choose epsilon equal to 0, that would give us no loss. The approximation would be perfect. But in say my epsilon is 0.01, then what that means is that my approximation factor of this algorithm is going to be 1.01. We're going to be able to come within an epsilon fraction of optimal. So this is the minimization form. We can also write the maximization form. And so, there's a couple ways you could write that, but the way that we're using it in this lecture is like this: the value of xa, so I'll keep the fractions running in the same direction this time, divided by the value of optimal, that's a t, is greater than or equal to 1 minus epsilon. Okay, so this is basically the same thing as saying, your approximation factor for a maximization problem is within an epsilon fraction of 1. All right. So this is fine. We need one more little definition to kind of round this thing out. And so we say this is a polynomial time approximation algorithm, or approximation scheme, if the running time of the algorithm is always polynomial in n for any epsilon. Okay. We say, this is a polynomial time approximation scheme, or a PTAS, if the running time is, for fixed epsilon, the running time is polynomial in the input size. So if the running time is polynomial in input size for every fixed epsilon. All right. And so, the kind of approximation, the kind of running time you might see for something like this would be, for example, a common one is big O of n divided by epsilon, right? So this is clearly polynomial in n. And then, as you see, the smaller epsilon gets, the slower the algorithm gets, like the longer it takes to run. So this would be one example of the kind of thing we might find. Another thing that shows up sometimes is big O of n to the 1 over epsilon. And so here, this is actually quite a bad scaling in terms of epsilon. So think about what happens if epsilon gets very, very small. Well, then you get n raised to a very, very large power. And so this is a case where it is exponential in the size of the error, but it's still polynomial in n. So that would still count as a polynomial time approximation scheme. But notice that just saying polynomial time approximation scheme doesn't guarantee that our algorithm is going to have good scaling in epsilon. It just means it has good scaling in n. So I have this guarantee that I can tune the error, but it's possible that things are going to be bad with respect to epsilon. So for example, this is technically a feasible running time for a polynomial time approximation scheme. So big O of n to the 2 to the 2 to the 2 to the 1 over epsilon, right? That doesn't violate any of our rules, but it scales very, very poorly in epsilon. So this is the kind of thing that occasionally you have to watch out for.